All right, in this video, I'm going to redo some of the things that we did in model theory to do kind of a more categorical version. So this video is about structures, signatures. Probably should have said signatures first. And Lawvere categories. So first we need to talk about operations on sets. So let's talk about some operations on sets. So this is going to be going into the signature portion. Okay, so let's give a definition. If S is a finite set, then S star, this is going to be called the clean closure. And this is essentially all possible strings. Made from elements of S. And so so usually it's considered with the operation of concatenation, and it has this thing here, epsilon, and this is the empty string. So this is the identity under concatenation. So this is the identity of concatenation. So you take strings and you can concatenate them together. So let's give an example. So if S is just this set with two elements, A, B, so then S star, this clean closure, so it's going to be the empty string A, B, A, AB, BA, BB, AAB, etc. Okay, and so there could be some notation here. So sometimes we might denote an element like this, like A squared B. And we may use, so we also may denote, AB by something like A times B. Okay, so it should look like a product. And the idea will be that later strings will be associated to objects of categories. Okay, so we can now define a signature. A signature, sigma, is a tuple of sets S, F, R together with three functions. One is, so the domain function here, let's say the range function, and then we have the domain of the relations. Let me get rid of that. This should be 2. Okay, so let me kind of give some terminology here. So the terminology. So I guess so okay, so F is going to be the function symbols. So this is what we call the function symbols. R is the relation symbols. And S is the sorts. Okay. All right. So there's some more. Let me just say this. I guess the idea is that dom F, R and GF, dom R will specify the inputs and outputs for functions and relations. Okay, so this is a way to cook up our formal symbols. I'm going to just say a couple more things about notation. So notation, some more notation. For f, an element of f, we may write this symbol here. So we could have this. So this is a list here to B. So where this is the here where this is the so, or we could write this as products, I guess. So this is the domain, and this is the range. All right, and so we may write sigma is equal to, let's say, something like sorts, functions, and relations here. And we'll omit this thing here. Okay, I guess what I also should have said is that this is going to be finite. So this should be, well, I guess these are finite strings. So that's okay. What else do we have? Okay, so this n here, okay, this n, this is called the arity of f. Okay, and okay, we also may write let's say R is a subset of for R a relation. Okay, so this is another thing we may write for if this thing here. So this is the domain of R. Okay, so this is the arity. Okay, the other thing that I wanted to say, the last thing I wanted to say, is if the arity of f is 0, then we call it constant. And then it's of sort, which is the range of f. Okay? All right. Okay, so now I want to talk about structures. But there's kind of another thing I can do. So let me give another definition. So let's talk about the Lawvere categories. Okay, and these are going to be used to talk about structures in a more categorical sense. So let's just make a definition. Let sigma be a signature. So then sigma will be sorts, functions, and relations. Okay. Then the Lawvere category associated to sigma is, let's call it sigma L, is the smallest category so it's kind of like the obvious category that you could construct from the information that I just gave you. So what will it do? It'll have objects such that it has objects for each S. Okay? It has, let's say, sub-objects, and I'll say what sub-objects are in a second. for R and R. Okay, so it'll all have subject, objects. Okay, so how does this even make sense? Well, okay, so for that to make sense, it needs to have products, so that this can be a subobject of the appropriate product of elements from S. Okay, so some particular strings correspond to products. Okay, and it has a morphism. So it has the appropriate morphism for each F and F. Okay, so we're going to build it so that this previous data of the structure here will be turned into a category where you have relations, functions, and these things, and then combinations of the strings will be there. So, all right. Okay, so now I have this Lawvere category, and I want to talk about structures. But first, I guess I needed to tell you about subobjects, because here I didn't say subobjects here. Okay, but we kind of know what subobjects are. They're monomorphisms up to an equivalence relation. So let me just say this again. So subobjects, so definition. So take C to be a category. And we'll take C to be in here, an object of the category. Then the subobjects of C will be equal to monomorphisms A to C modulo some equivalence relation. Okay, so what's this equivalence relation here? Let me talk about this. So we'll say that some map here, A to C of F, will be equivalent from A prime to C. We'll call this F prime. So we have two inclusions, if and only if, so there exists some G from A to A prime, such that the following diagram commutes. So we have A prime, C, this is F prime, we have A, this is F, and then A to A prime, this is G. So that this map factors through here. So that's the notion of the equivalence relation. And so I guess what you can do is you can check that this is an equivalence. Okay, and then so I also wanted to say that so some notation. Let me just say some things about notation. So we're kind of going to abuse notations. This will denote both a monomorphism. So the abuse is that this is a monomorphism and a subobject. Object. Okay, and sometimes people like to do the same thing with this notation. Okay. So. Well, why am I talking about subobjects? Okay, so first of all, I just want to kind of say something else about subobject while we're on it. So eventually, kind of a interesting point. So if C is a topos, and so e.g., let's say C is some sheaves on some site here, then for some object in here, then this thing here will be a lattice, and the idea will be that the top value of the lattice will correspond to true, and the bottom value will correspond to false. So in in the setup where we're going to do logic, which is valued in a topos, the sub-objects of certain elements, so these things will form a lattice, and this is where we're going to get truth values. Okay, so that's one thing I just wanted to mention. That doesn't really have to do with the structures that I'm defining right now, but while I'm talking about sub-objects, it should be mentioned. Okay, so this is the sub-objects here. So this is what I just defined. Okay, so sub-objects are monomorphisms modulo this equivalence relation. And the equivalence is that they factor through each other. Okay. So we're still on structures. So definition. Okay, so given a signature, we're going to construct a structure. Okay? So the idea is, given a signature, we construct these category of structures with values in another category. So usually these are valued in sets, but we're going to do it with another category. Okay, so let sigma be a signature. Okay, so there's the short. I'm going to kind of do this in two ways. So the first way is a short way. Okay, so the objects of we define given a signature, we will construct a category. Of structures with values in that category. Okay, so how are we going to do this? There's kind of a short way. The short way does the following. So the objects, let's do a double underline, a single underline here. So the objects here are, well, they're going to be functors from the Lawvere category to C. So they're functors, we're going to do it like this, the notation superscript M. And the morphisms are going to be natural transformations. Okay, so this is quick. But let me just say something else about these functors. So they need to be monomorphism, and product preserving. Okay, this is the short way, and now I'm going to kind of spell this out. So the long way to construct the objects of this category. So we have these things, and we have these natural transformations. Okay, so the longer way. So long way. Okay, so we want to. It's going to be. So what these things are interpretations of the signature. Okay, and here's how we do it. So we're just going to give a bunch of data. Okay, for each sort, okay, we give some object of the category. Okay, for each. So this is kind of be redundant, but it's okay. So for each string here, a long collection of strings, we're gonna we give the following. So if we take this string here, A1, I'm going to write it with commas now, dot, 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 AN, and we apply M to it. So this is just going to be, since we want it to be product preserving, it's going to be like this, AN to M, okay? For the empty string, so this is the empty string. We take epsilon m to be a terminal object. Of C. Okay, so what I forgot to say is that okay, so here so C needs to have, I need to say this, C needs to have products and a terminal object, a given terminal object. So we're going to show that we're going to prescribe the terminal object, not that it exists. Okay. Okay, so this is what we do, and then okay, so we have this to be the terminal object, and okay, so we have two more things. So for f, so in f, so this is a function. We take fm, a1, an of m, bm, a morphism in C. Okay, and then the last thing is, I don't know if I have room here, for R, a subset, or so one of these relations. So I'm kind of mixing notation here. This is probably not very good, but we take Rm in A1 to the M, An to the M. So this is going to be a subobject. Okay, and this could be maybe the inclusion. So in the categorical viewpoint, where we set up the Lawvere category, we could call this I sub R. So that's the inclusion of this into this. Okay, so all right, so these are the objects here. So these are the objects. Of the structure, these C structures for the signature sigma. Okay, and then the morphisms. So the morphisms, maybe I should do it in blue again. Let's see, this blue. The morphisms. Okay, so what are the morphisms? So the morphisms are a collection, so a morphism of structures, H M to N, is a collection of morphisms. Let's say HA from AM to AN, I guess for A in S, such that two diagrams commute. Okay, so first one, and then we'll try and do two here. Okay, so the first is that for all functions function symbols, we have the diagram that you'd want to write. So this thing goes like this. Here's B. This thing also goes like this. A, N, B. Okay, so this is interpreted, this is F. These are interpreted with M. These are interpreted with N. Okay, N. And then here we have this HB, and then this should be a product of a bunch of things. So HA1, HAN. And so that this thing commutes. Okay. Okay, and then the second diagram is about the relations. Let me go back. The second diagram is about the relations. And it says the following. So it says for every relation, or let's call this here, A1 cross AN. So this is a relation symbol. So we have R, and then we have this inclusion, IR, and this includes into A1, AN. And then we have this, because we're going to write down the exact same thing down here, because we're writing down a commutative diagram. Okay. So this is M, M, N, N. This is I, R, N, here, and here. And this thing is, okay, so I should say that this exists. Okay, and so we're saying that this thing exists so that this whole thing commutes. Okay, I guess you can ask whether this will be given or you would find it. I think we should say that this will be given as part of the morphism. Okay, so this is what it is. This is exactly what a structure is. A structure is, so the objects, the C structures are these objects which kind of interpret the structure, and then the morphisms are what you'd expect them to be, kind of natural transformations. All right, and so let me just remark, if C to D is is monomorphism preserving, monomorphism and product preserving, let's call this phi. Then we get an induced functor. Okay, so I guess the structure thing is a functor from the category of categories with terminal objects and products, right? And then the morphisms in that category are product preserving and monomorphism preserving functors. Then the structure thing is a functor from on these categories. Okay, and that's the idea of what a structure is. Okay, so now we've just talked about structures. Whew. All right. Thanks for watching this one.